Okay, so as we all know, we are here for the presentation by Aseem Gupta. Before we go into the presentation, let me just talk briefly about our chapter. So the chapter is Santa Clara Valley chapter. We have George as vice chair. She is our secretary. We have treasurer Haiming. Then Imran is our webmaster and e-notice. We have few industry liaisons, Jonathan from Qualcomm, Robert from Renesas, and then YK Chen from Alibaba. Then we also have the Facebook page where we kind of post everything. You probably get on the notice as well from the e-notice. It's also there on the Facebook page. This is our website. I encourage to sign up for the volunteers. I mean, at this point, maybe very soon we will be having somebody waiting. We'll be having in person, and hopefully then probably we need some more volunteers. But please welcome to join us anytime. Sign up for the and then as I said, we actually were posting a lot of lectures on the IEEE TV, but I think it's still kind of some hassle to go through it, kind of pass on everything. So I think from now on, what we're going to do is we'll probably put on our YouTube channel, and hopefully we'll get more audience from worldwide audience. And future events, I'm pretty sure everybody knows that at this point, ISCAS is going on. So I kind of removed that slide. And I think today's the last day for the ISCAS. But the one conference coming up is the flagship event of the circuit system, that is the Midwest Symposium Circuit System. That's actually now almost fully virtual. So that's going to be in sometime in June, so first week of June. I think the conference is late, sorry. It's probably in July, in first week of August or something maybe, yeah. And then one of the, we are honored to have a distinguished lecture from Professor Trajkovic from Simon Fraser University. That is on data mining and machine learning for analysis of network traffic. And that's the next June, 17th June. Everyone is welcome to register for this event. So let's go back to the our main topic of the today. And let me introduce the speaker. Aseem Gupta received his MS degree in electrical and computer engineering from Stony Brook University, New York in 2015. He's currently a staff electronic engineer at Stanford Linear Accelerator Center, SLAC Laboratory, Instrumentation Division, Stanford University. He was also a staff research associate at Brookhaven National University, New York from 2015 to 2017, where he worked on development of readout logic for triggering the digital LO buffer for ATLAS, Atlas, experiment at CERN, Geneva. He is currently focused on development of waveform digitizer ASIC operating at cryogenic temperatures for neutrino detection in time projection chamber, the TPC experiments such as Deep Underground Neutrino Experiment, Dune 87K, minus 87K, and sorry, 87K, 87K, and next enriched xenon observatory NEXO 113K. His research interests are in high-speed LVDS driver, cable measurements, integrated circuits, and design of backend architectures with digital on-top methodology in mostly analog ASICs. He has authored, co-authored in various conference publications, and he's as well an active IEEE member. So with that, I welcome Aseem. Please share your screen.
Thank you, Amit. Thank you for that elaborative introduction.
Sure.
My name is Aseem, as you already know now, and I am design engineer at SLAC, which is, again, I'll say Stanford Linear Accelerator Center. It's part of Stanford University, where we have a dedicated team to design some electronics for high physics high energy physics experiments. And today I'll be presenting on the project I've been working for the last couple of years, and probably all the people here are probably our team right now. Then and now, some people are there. In this talk, I already see three people connected from our team. That's good motivation. So Before I can probably dig deep into the slides, I would just give you a brief introduction, just probably share the website of our company, just to give like a little idea what we do. It's a research laboratory, as Amit was saying, and as I can explain, because it's been 4 years for me at SLAC. And here at SLAC, we have great facility in terms of physics, high energy physics, biological experiments, chemical experiments. It was built in 1960s as one of the initial linear accelerators. It's like 1.5 mile long linear accelerator stretching from, you can see right now live on the screen, this is 1.5 miles going from Menlo Park to the foothills of the mountains across I-280. You might have passed sometimes driving over that accelerator. So yeah, a lot of cutting edge research is going on in high speed X-ray, and a lot of scientists from all across the world. They use our facilities in near Hall experiments and far Hall experiments to dig deep into their experiments, to study deepest molecules, deepest chemical reactions possibles. And we, as a team, we have right now a great mentor, great supervisor. His name is Angelo Dragone. He has been running ASIC design team for last 13 years at SLAC. And we are right now currently 8 people in our team designing camera, CMOS cameras, sensor readouts, and cryogenic application chips, as I'll be talking more in this talk. And this talk, I would also like to probably thank before Aldo, who has joined here, who's the mentor for the CRYO project, and I've been part of the readout process, which I'll be explaining in detail now. So we will start with some motivation, like what motivated me to take this project, or what motivated us to take this project at SLAC, and then give you some introduction about the CRYO project. And then I will dig deep into the digital part, which I have specialized in, and with the help of my colleagues, and probably designed a lot of modules to read out the charge. And then I will talk about verification methodologies and show you some simulation results. And at the end of the talk, I will conclude. So let me put it in the PowerPoint mode. Okay, perfect. Okay, great. So let's start with what motivated me. We all know what motivated what motivates this project, let's say. So we all know, like, scientists all across the world, like maybe it's in the CERN or some other research laboratories, are trying to find the answer of only one question, that how did we all arrive? Why did the Big Bang happen? And what is the origin of matter? And then what is this universe made up of? Like, what is the smallest particle? Could neutrinos be the reason that universe is made up of matter? Or maybe something else, like it's universe is not matter, it's antimatter. So we need to detect neutrinos, which give us great insights of the basic building block of the matter. So a lot of experiments have been going on since decades about this subatomic phenomena. And 2 of the leading experiments today, I would say, are DUNE, which is the Deep Underground Neutrino Experiments, and the Next Enriched Xenon Observatory, which is abbreviated as NEXO. So I have been designing for both, and it's a great collaboration between US and Europe and all across the world. There are collaborators who are working on this project. They are global experiments for neutrino science and proton decay. So what challenges it comes, like we need to design robust electronic systems because to detect neutrinos, we use this technology called time projection chamber, which has been there for a time now. And this is a great detector technology, which helps us reconstruct the events precisely. and it helps us identify where is the particle present, neutrino particle present. But the thing is that these detectors, these time projection chambers, they work with cryogenic liquids. That's why the name cryo has come up, because they deal with liquid argon, liquid xenon, and I would say, as we can see in this image here, Dune is liquid argon, is taking liquid argon as the basic chemical, basic cryogenic liquid. And what is going to happen in Dune? Let me give you a brief overview here. As we can see, so this is Fermilab. This is in Chicago. You might be knowing Fermilab is a great facility to work. And from Fermilab, they have a proton accelerator there. They're gonna inject the neutrino beam. They're gonna produce the neutrinos here, and then they're gonna travel at speed of light, which is they're gonna travel at speed of light for almost 1,300 kilometers, 800 miles west of Fermilab to a facility in South Dakota. It's called Stanford Underground Research Facility. And there we are building this detector, underground particle detector, to detect those neutrinos. So our chip, our electronic systems is going to be placed here. So technically CRYO is going to be placed at this location. If you can see my mouse, excuse me. So the challenge comes, since this is all underground, we need to bring the cables to a data acquisition system placed here in Stanford Research Facility in South Dakota when we read the neutrinos. So to have those long data communications, we need to build a chip which could drive and read out the data. So CRYO ASIC is one such solution. It's a solution which is system on chip with waveform digitizer and serializer on there. They're on chip LDOs, they're on chip pre-emphasis circuits, drivers. So it's a great solution to have detection at this point. And then it also drives along cables to a facility for data acquisition here. It is optimized for cryogenic temperatures, as we talked, 87 Kelvin, which is negative 186 degrees Celsius for Dune, which is a great temperature. And I think we have tested it. Our chip is being tested these days. So I will talk more about it later on. It's built in 130 nanometer CMOS process. One great thing about this project is that Aldo and one other colleague, we all work together to extract the models in-house at this such cold temperature, because we all know Foundry doesn't provide models for negative 186 degrees Celsius or 87 Kelvin. So those models were extracted in-house, and then they were tested for reliability and durability purposes. Other thing in this chip is that this chip is running at 20% lower supply than the nominal 130 nanometer process for reliability purpose, because this is going to work for decades. So let me introduce a bit about the CRYO ASIC. CRYO ASIC basically comprises of three big portions. It's, as I told you before, it's a system on chip. So it has an analog front end, it has an ADC and digital backend, everything in one chip. And I have been working on digital backend, and I will explain more about digital backend in this presentation. But to give you a brief overview, it is 64 channel ASIC, which is smartly divided into 32 channels of two banks of 32 channels. And then each bank is giving one data stream out. Each channel has a dedicated analog front end with its charge preamplifier and filters designed. We have the main designer here, Aldo, who has designed the analog part and the ADC. And then there are across four channels, there is one ADC. It's a 12-bit SAR ADC, which takes the charge and converts it into digital code, and then it's read out through a single data stream via backend, which I'll talk more about in this. So the ADC as such contains sample and hold, a signal driver, and a 12-bit SAR ADC, the analog digital converter. And that output of that is processed through a backend module. Now talking about the detailed backend module, we have a lot of modules here. We have an on-chip PLL, which takes the 56 megahertz input clock. We have a digital sequential multiplexer. We have a customized encoder, 12-bit, 14-bit, to encode the data for DC balancing. Then we have a serializer working at double data rate, giving the throughput of almost a gigahertz. And then we have LVDS transmitters to drive those long cables. And then I would talk about in the slide coming later about the pre-emphasis techniques which we have developed to drive such long cables. It's tens of meters of cables. So one other thing to note here is that since this is a subsystem on chip, we have immersed the entire digital backend in a deep in-well trench to suppress the coupling of digital noise going into the n-log domain. Let's talk more about the architecture of these modules, digital readout. So this figure talks about the basic block diagram, the basic of the digital backend. As we can see that the data comes from ADC, 12-bit ADC, data is arriving. And then as this data is latched, we have digital multiplexer, which sequentially selects the data out of these 8 ADCs and selects only one data. And then it encodes it, as we can see here, serializes it, and then passes it to a level shifter and then driven by the cable. But the flow starts from here. Technically, if we start from the bottom right, we have a master clock. We have a master clock going into the receivers. It's a 56 megahertz master clock. It's LVDS, and then receiver makes it single-ended. It gets level shifted. And then this is received by the PLL. PLL actually obviously has a 1 to 8 frequency multiplier. So it converts our master clock from 56 megahertz to 448 megahertz PLL clock. And then this clock is passed through this module called clock generator. Clock generator generates all the clocks required for these small modules like multiplexer, encoder, serializers, and for other smaller cells like the latch. And then we have two more control signals. It's called sample clock enable, which gives us an indication that now we need to enable our clock where we need to sample our ADC data, and start readout, which tells us that now we need to start the data acquisition. So once these signals are these clocks are generated, we can see that the DMUX clock is 64 megahertz. The sample clock here is 8 megahertz because ADC is 2 megasamples per second, and then it's taking from 4 channels, so it's 8 megasamples sample clock. Encoder clock is 64 megahertz, and serial clock is 448 megahertz, but it's working double data rate, so the throughput becomes 896, almost a 1 gigahertz throughput out of serializer. So this gives a basic block diagram of our digital backend. And then once we have the drivers, we have this cable, which was important part. I will explain more in later slide. That modeling the cable was very important. So we faced some challenges, but technically we were able to extract some S parameters, mixed mode X parameters of the 25 meter twin X cable to see how much was the attenuation coming in and coming out of the 25 meter cable to see how much voltage swing we wanted with an output termination of 100 ohms. So yeah, these are the steps we followed. We designed, we simulated this, and we saw a nice NI diagram at the end, which we will see the results. So let's talk about the timing of this ASIC, the digital readout timing. So as I said before, we have a master input clock, which is going into PLL, which is 56 megahertz here. PLL converts it into 448. And then ADC, the SAR ADC, it sends end of conversion signal to the backend, saying that, okay, I have finished converting all the analog signals to digital codes. And now you can sample the data in the next cycle. So once we receive the start readout from the FPGA, when it's asserted, the encoder, 12-bit, 14-bit encoder, it starts trimming out idle patterns to lock the digital system to synchronize it before we can read out the actual data. And these 14-bit words are just like comma characters, idle words, which has fixed values, hex values. It's just used for synchronization with FPGA, as I said. And then there's one extra comma character called start of frame, SOF, which tells us, okay, now next incoming data would be actual data, the real data from ADC, not the idle data to synchronize. So which tells us that now we need to actually stream and then read the data. And then these data packets are serialized. These are 14-bit data, right? So then they are serialized. And then the bit stream is outputted out of that, the chip at 896 megabits per second, which is our throughput. So this is the very important module here. We designed our custom encoder. It's a 12-bit, 14-bit encoder with a wrapper around it. So let's talk about what is a wrapper. Wrapper has some test patterns. Wrapper has different testing modes. So we kind of included some modes just for calibration purposes. And then we had a couple of multiplexers just to switch between different modes. So I'll tell you, mode 0 here is the main mode where the data comes in from the ADC, which is sequentially selected by the sequential digital multiplexer, and then it passes through the encoder, passes the entire chain. That's the entire chain of the backend. Digital multiplexer, encoder, serializer, LVDS transmitters, and the cable. And then we read the data out from there. Then there are some test patterns which bypasses which they don't come from ADC. Like they are the test patterns generated by a pseudo random generator coded digitally, and then they generate certain patterns, as you can see, like A's and 5s, 0s and 1s, and then that is encoded, and we see that the chain is working. We have some which bypasses the encoder just to see if the encoder just for debugging and calibration purposes. So we have these modes. One thing I want to say here, that this entire wrapper along with the encoder was done fully digital. RTL code was written, and then it was synthesized, and it was placed in route using Cadence tools, latest tools, Innovas, and the entire area just came out to be like 200 by 70. Here it's a snapshot of the from the Innovas place and route tool. So it's a fully synthesized logic for the encoder. Let me move ahead. So verification methodology, right? So verification becomes really necessary because there are a lot of modules involved, and we need to test that if the data is actually stream coming out is actually the stream we are sending in, the data we are sending in. So it becomes very necessary. So with help of another colleague also in this call, it's called Lorenzo, we developed a nice custom Python and decoder because we are getting encoded data serialized. So first we deserialize the data, then we decode it, and then we see that if it matches with the input data. So they were written in Python at the software level, and then data integrity becomes really important because we are driving a 25-meter cable. So at the end of that cable, we saw that stream, and then we deserialized, and then we decode. So we are actually testing it at the end of the cable, so we don't lose any integrity in the data. And then we did several test cases. 3 of them are described here. We tested with an input called Sinewave. Okay, let's provide a Sinewave, and then let's see if the Sinewave comes out of the cable. Let's provide some fixed values in digital from 0 to 4095 because the ADC is 12-bit. And then let's provide some constant ramp and see a ramp coming out. And then this verification methodology was done across corners. As we can see, the verification flow, again, is the 12-bit data from 8 ADCs coming here, selected by this sequential digital multiplexer. And then 12-bit data is encoded, serialized, is then driven by the driver. At the end of the cable, we go to the verification flow, deserialize, decode, and then if they're equal, they're matching. So that's how we conclude the verification was fine. So we match against the defined inputs. So let's talk about all these 3 sets of input. So first one is sine wave. So it's coming from ADC, and then again goes through the flow, and then we saw a sine wave coming out here. It's very nicely, like whatever we provided, we saw the codes going from there, and then this was plotted in MATLAB, and then we saw the same input was coming out of the end of the cable. So this means the verification was working. So it's a digital multiplexer sequentially selects the data, and sends to encoder and then we saw the stream coming out. It's exactly retraced at the output. And then we tested with random numbers, random digital code values, fixed numbers like I provided some samples, 300, 1100, up to 4095. 8 inputs were provided, and then those exact values were seen at the end of the cable when they were plotted after being deserialized and decoded. So this established the verification flow. And this was a constant RAM where we were providing. And as I explained in the encoder modes before, let me go back here. There were some test, sorry, I think I'm going forward, not back, okay. In one of the modes I explained, right, that we have some test modes. So the mode 3 was the ramp mode, where we were providing a ramp. It was not the actual data. So I kind of tested that mode also and tested our verification flow in the third one, where I'm providing a ramp here, not providing the ADC data, but providing a test mode to the encoder. It passes again to this flow, and then we see a ramp in the MATLAB. So we did several cases, but these 3 are shown here. And then we established the verification flow was working fine. Now coming to the very important part of the experiment as such in CRYO, in this Dune experiment, as I was talking in the first figure we saw in South Dakota, in the Stanford Research Laboratory, we have this underground particle detector. So from there, we need to take the data out into the data acquisition room. So this room is on the cold side. This room is on the warm side. The TPC is at the cold side. 87 Kelvin is really cold, right? So we need to drive that data from the cold side to the warm side. And then for Dune experiment, this could be tens of meters. It's not tens, it's 25 meters. For next experiment, it's up to 10 meters. So this was a challenge. And then we developed our own cable. It's a 100 ohm output termination, twin-X cable. And then we wanted to model the insertion loss going from the cold side to the warm side. And we noticed, obviously, it's very obvious the signal strength was deteriorating over the length. It's a 25-meter length for Dune experiment. So we wanted to measure the S parameters for the insertion loss. Can you guys hear me fine, or there's a disturbance going on? I think somehow.
I can hear you well, Aseem. Let me see somebody. I think someone is.
I was unmuted.
Hi, so, Steve. Hi, Steve. Can I mute you, Stephen? I'm going to mute him. Okay.
Thank you, Amit. Sorry about that. So yeah. So the idea was, to measure the insertion loss in the cable for 25 meters. So we used the instrument called Vector Network Analyzer. And then we modeled the insertion loss at room temperature. And we saw that there was a considerable loss, like the amplitude reduced almost 4 times. And then at that frequency, as we can see here in this graph, this is coming straight out of that Vector Network Analyzer. And this image shows the image of the cable we used and the cross section here of the twin-X. So at 896 megahertz, 896 megahertz, we had insertion loss, which was almost 20 dB from input to the output here, frequency 1. And then this amounted to be 12 times, this amounted to be 4 times loss. This was 12 dB loss. And then 4 times in amplitude loss, technically, like if the swing was suppose 600 millivolts, the swing reduced to 150. And then to compensate, we had to come with a strategy called of pre-emphasis, which I'll explain in the next slide. So we all know the standard LVDS drivers, like low voltage differential signaling. They provide 3.5 milliamps output data current. So the swing becomes plus minus 350 with output swing, 100 ohms termination. LVDS could be good up to 3 to 5, but then I think we need to go for maybe CML logic or something. But signal attenuates over the length of the cable, and this was 25 meter. So we kind of had a pre-emphasis circuit working in parallel with the driver, LVDS driver transmitter. With a delay logic, we kind of developed it and kind of fine-tuned it for our needs, for the bias currents and for the lengths we wanted. And then by doing that, we were able to get the swing back whatever the cable was inserting as a loss, we were able to get the swing back. So what emphasis that, like, it speeds up our edge rate at the edges and also provides a bit of overshoot in the current. That's why the voltage swing increases. So if there's a great reference about pre-emphasis circuit, we can probably, I will show you then the reference which we pondered over and then implemented our own custom pre-emphasis circuit to drive, and it's programmable. As I said before, that we can tune it for different currents, bias currents, and we have fine-tuned control there. At the end, these are the results obtained in simulations. We were able to plot the eye diagrams at the end of the 25-meter cable. And this shows 3 different temperatures starting from room in the left, and then the next, which is the colder and the coldest, the dune, 87 Kelvin. And then we can see how the output voltage swing is increasing while decreasing the temperature. As we go cold in temperature, the current strength in transistor becomes more, and then the swing increases. And then we measured that the jitter at the dune temperature, which is our main focus of the experiment, was 29.3 RMS jitter. Peak to peak is 0.15 of the unit interval. Unit interval here is 1 nanosecond because we are running at 1 gigahertz. And then we were measured almost like an open eye with 400 millivolts at the end of the cable after the pre-emphasis. Here, the bit period was 1 nanosecond. We are running 1 gigahertz. So these were good results. And then the chip is in testing now, and we are getting some measured results these days. So I will probably conclude with this that we were able to design a robust backend architecture for the TPC, for the cryo experiments in 130 nanometer. We were able to read out the data properly at high speed, as the title of this talk says, at high speed at 1 gigabits over long cables, up to 25-meter cable. And then S parameters, another interest of mine, modeling the cables were obtained to take into consideration the insertion loss introduced by 25-meter cable at that speed. And then we showed some eye diagrams right now in the previous slide, with the jitter was measured as 29.3 picoseconds RMS and 0.15 UI. But I want to say that this was achieved at dune temperature. This was the best case for us. Like, if we go back, we had lower or higher jitter and lower amplitude for room temperature, but then at cold we had best case here with on-chip pre-emphasis circuit. So driving at 1 gigabits per second, the data. So at the end, I would say that fully functional readout process was achieved at room temperature and cryogenic temperatures, both NEXO, which is 113 Kelvin, and dune, 87 Kelvin, the coldest temperature. Sorry, 160 Kelvin, 113 degrees Celsius, making the architecture suitable for noble liquid TPC detectors. So we were able to achieve the readout process. We were really happy. And I would again thank my team, especially Dr. Aldo here, who has joined and who is the main pioneer of this project, working in analog front end and the ADC, and also helping me on the digital backend. So these are the references. Please feel free to go to our Dune collaborative websites and Nexo, which are the great experiments going on with the help of Stanford and people from Europe and Fermilab. So this really tells like we have an opportunity to find neutrinos, and this was the main idea about these experiments. And I thank you all for listening me very patiently, and I would probably welcome any questions from your side. And I thank you from behalf of our SLAC TID integrated circuits team now. It's instrumentation division now. We kind of changed to, it's not AIR, it's now instrumentation division. Thank you.
Okay, thank you, Aseem, so much. So if people have any questions, let me see the chat. I don't see question in the chat. So yeah, we'll be taking questions. If anyone has, please go ahead.
I have a Question, I may have missed it, but what do you define as a long cable? 25 meters?
Yeah, for us, it was pretty long.
Because it doesn't sound too long.
I mean, for cryo applications at 1 gigabits was already long, because we have been testing for smaller cables and driving data at cold. I mean, I understand for room it might be not that long, but driving data at cold was pretty challenging for 25 meter at 1 gigabits per second.
Do you happen to know what might be a high end? What's the longest that might work?
I am not sure. I think in this cryo field we have the longest.
Oh, okay.
So, but I'm not sure. People have done until like tens of maybe 7 to 10 meters for next experiments, but this was a requirement for the Dune project, and we were able to drive it.
Is there something you can do as a next phase or next step?
To go even longer?
Yes.
Well, we have to design a different driver, I would assume, and with smarter on-chip emphasis techniques, because right now it's LVDS and it has some limitations on the swing. And probably there are scope, yeah.
Okay,
Thank you, George. Yeah.
So on the same thing which George was asking, could you use like a CML driver, get more swing at the driver? Because I think you said that you wanted to use CML driver at 130 nanometer. Yeah, I don't think you're still burning a lot of current there, right? Your driver is still kind of looks like 3.3 milliamps, something like that. You said.
3.5. Yeah, the swing with 100 ohm termination became plus minus 350. Yeah, it's not a lot of current. That's why we went for LVD. It's not that we wanted CML, but if the requirement was more, maybe there is a chance with CML if you want to drive, let's say, longer cable at 5 gigahertz tomorrow. So I would assume that this will be the new new driver. I think LVDS would have some limitations up till some gigahertz, 2 or 3 gigahertz. This is my understanding. But
and this is all CMOS process, or is this like a kind of a bi-CMOS, or just a regular CMOS process, 130 nanometer?
Oh, it's a regular CMOS, like all native transistors. Yeah.
I see. Okay.
Like we have some low voltage, low threshold voltage transistors. We have nominals. Yeah.
I see. Okay.
But it's.
Yeah. Okay. I got it. Okay. Thank you.
Are there other applications for your process?
I mean, it's a waveform digitizer. So technically, I mean, you could use it as charge readouts chip, right? So I mean, the full chip is working as taking the charge in some form and then reading out as the data. So, and it's at A to D ADC, analog digital converter. So I think it's pretty general, but it was dedicated to for certain specifications which the Dune experiment required. And then we tailor-made those front end and ADCs and the digital backend according to those specifications in terms of detector capacitance and readout rate and the dynamic range we want to read out. Yeah, but I assume that this is waveform digitizer, so it could be probably used.
Yeah, thank you.
Yeah.
Hello, Aseem. Thank you for the presentation. May I know why is 25 meters spec? Is it because the TPC, is it underground or somewhere that it's far away and you have to drive the cable?
Yes, very good question, Haiming. Thank you. I think it again comes back to the requirement given by the experiment because this detector is kind of nicely physically located here underground, as we can see in South Dakota. It's a Stanford research facility, and then data acquisition was already on the warm side, and this is the cold TPC side particle detector here having the cryogenic liquids. So we wanted, I mean, it would be in progress. I would say that it would be read out right now once we get the chip and then install it and all. It's a still ongoing research project, but we are getting good progressive results here.
So for the 25 meters, there is no repeater.
Sorry.
Is there a repeater inserted in between?
Repeater, there might be at the system level, but at the ASIC level, I mean, we did not have anything.
Yeah, it was, yeah, 25 meters, quite long. Well, I don't know what you're driving, what voltage you're driving it at.
Yeah, it's 1 volt here.
1.2, something like
1.2.
that.
Yeah, but
Yeah.
20% less. So
I
yeah.
see. Yeah, have there been any thoughts of just putting your ASIC into cryogenic environment?
Yeah, I mean, I think right now, once we tested our local systems, then I think this is the next thing that we go to South Dakota and start testing it there with the real detector, with the real TPC, and then reading it out at this facility
Yeah,
here.
because this is some of the suggestions that the quantum computing guys are trying to get to. They're studying the CMOS characteristic under the 70K temperature kind of environment.
Under 70K. Yeah. I mean, yeah, I think it's an upcoming field, all this quantum superconductors and low temperatures, cryogenic temperatures. But still, we saw some good simulation results. And then I hope that, we are able to, actually install the chip in the TPC and see the results, measured results soon. But we'll give you an update, definitely.
Thank you.
How exactly did the low temperature make things more difficult? Does it increase the insertion loss of the cable? Does it reduce the speed of the drivers? Did it reduce the amount of power you could pull, like limit how much power you could consume?
I think we had a constraint on the power for sure. I don't think that the temperature restricted us in the insertion loss. It probably helped us there. But the restriction on the cold temperature was actually in terms of the current strength and the drivability to extract the parameters, and then to have the durability over a couple of decades was the big challenge here, because we are running lower voltage supply for durability just because it needs to work for long. And then models were not there across corners. So that was another challenge.
Thanks
for the cold. Thank you, Ron.
Any more questions?
I have a different question. Do you happen to know what the upper and lower limits of neutrinos would be that would be affected by?
You mean the count?
Yeah.
The count of how many could be detected in this? I'm not sure.
I mean, the error might be more if the count were very high, for example, right? So.
Yeah, that's a good point, George. Yeah. And then I'm not really sure about this, because scientists are, more into the device physics level and all these neutrinos. We as engineers are probably at the more ASIC level, not system level, or like more experimental level. But if I come to know, I will definitely, get back to you on the count and how does that affect obviously the readout. Yeah.
Okay, thank you.
The error rate. Yeah.
Right.
And similarly with Nexto, I would say this is also a great experiment. It's using liquid xenon at a warmer than Dune, but still very cold temperature, 160 Kelvin, negative 113 degrees Celsius. So yeah, I mean, people are still working at Stanford for this. It's a great. I mean, I think in a couple of years we'll have good results from Nexo too. Yeah.
Okay. Aseem, I have a couple of more questions. So
yeah.
if you go into the waveforms that you showed, the eye diagrams.
Yes.
Right. So these are measurements done by the VNA at those temperatures?
These are the eye diagrams plotted by our tool we use for design.
These are not measured.
These are simulated results.
These are similar measure. Oh, I see. Okay.
Yeah. So yeah, this is not by the vector network analyzer yet. Yeah.
Okay.
So not but the chip is in. I think it's now being tested these days. Yeah.
Okay. Also, you talked a lot about the modeling of your cable. So how do you model when you go this temperature, there's a temperature gradient, or like what, can you give us some more, a bit analysis
Yes.
that
Yeah.
went there?
Great, Dr. Amit. Thank you for this. I mean, this one, as I said, it's at room temperature, these models. We did not go cold. Colder would help us to answer Ron's question before. So these were already very conservative like results for us. So we wanted to, have the worst case. So we did not go cold with 25 meter. It was not possible. Or maybe that time the pandemic was hitting and going into the room and all was a big challenge. But yeah, we had a calibration device which used to calibrate the ports. It's like dual port network. When I was doing it, like we had S12, S21 is what the mixed mode parameters, S22, and then you see you do the mixed mode analysis, and then extract the parameters to see how much the loss you're seeing in terms of dBs, and then relate that with the bandwidth, the rise time equation to see the amplitude reduction. So that we did that. I think we knew that this was room temperature and cold is anyway going to help us. So these were anyway the worst case conditions for modeling the input and output of the cable for that. And then we did measure later on. It's not in this presentation. We did measure on smaller cables and saw a trend. Like we did measure on a 5 meter or 10 meter cable with the same temperature. So we did not have a temperature gradient to answer your question per se in this, because they were all tested at one temperature, room temperature.
I see.
But that would be our next step, once we are actually doing it now, since we have chip came back from fabrication. So it's been tested these days, and then this will be we will be doing it in sometime soon.
Okay, that's great.
Yeah.
So yeah, I have one more question, but if anyone else is waiting, I'll let them go before them ask question before I ask.
Yeah, Aseem, I was wondering, is there any optimization as far as the type of cable you use? Maybe some kind of software correction or some kind of lookup table correct for the loss?
No, we don't have like a correction at the system software level. But this kind of, followed the trend. We did this 2-3 times and calibrated it. Excuse me, like the instrument is pretty like robust enough to measure much more frequency, like up to 15-20 gigahertz. So we kind of saw that okay, this trend was a nice trend, and then we have great people who are working in different experiments who are running even higher speeds, and then they helped us in this too. So it was nice to extract those parameters. But yeah, but we did not have a software correction as such. It was this graph is straight coming from the screen of the instrument. Yeah.
Thank you.
So where is the chip fabricated? I mean, yeah.
It's coming out now. I think it was in 130 nanometer. So it's we will test it. Yeah.
I'm just asking, is it actually manufactured, not fabricated in Stanford?
No, we send it out. Yeah, we don't have the facility.
Yeah, I just wonder, how do you actually get the different temperature characteristic? Because do you actually need a process, or is it just the one end of the input?
For the chip,
for the eye diagram they're showing.
For this one?
Yeah.
So I didn't.
Is there any part of electronics that's under like 160K or 87K?
Oh no, these are all simulated results. Like the chip just came back, and so we like last week. So okay. this talk was scheduled sometime before, so we didn't have that result. Obviously, it will be coming out. So if I get a chance again, thanks to Dr. Amit, I would be willing to present the measured results. Yeah, in some time. Nice. Yeah. Right now the chip is not in cold.
I see.
This version which I'm presenting, yeah, the one with
driving. You have some model, right, in order to simulate it.
Oh yeah, we started the models. That time we went cold for sure, and this is the second iteration. So the previous iterations were not driving that longer cables, and then we made some changes. So yeah, the models were started at cold for sure. So there were some test structures All the devices like LVTs and nominals were for P channel, N channel were tested in cold. And then we had a model started, but the chip, this particular version of the chip has not been gone cold, but we have a previous version, but that was not able to drive a longer cable.
I see.
We made some logical changes with emphasis and this to drive that longer cable. Yeah. But the chip has been to cold for sure last year. Yeah.
Yep, thanks.
Thank you, Heming.
Okay, so I guess if nobody has questions, then maybe we can just all thank Dr. Aseem Gupta. Thank you so much, Aseem. It was lovely
Thank you.
hearing your
Thank you.
talk. Very interesting. And I'm sure we can schedule one more talk sometime later when you have, all that the data that you've been talking about.
Yeah,
So
and
that'll be great to know. I'm also very interested in, how did you get some of those transistors, like you kind of touched upon it, like, some of those models, like how did you change the mobility stuff, or did you change the, like kind of like how did you, because your temperature range is extremely extreme, right? Your range goes from 87K to 300K. So your modeling tools need to be really good to some level of accuracy that you're kind of expecting. So that's a huge challenge, my understanding is. So anyways, thank you so much. And hopefully everybody enjoyed the talk. It was a great talk, I believe. So
thank you, Amit, and thank you everyone for joining. And I thank my colleagues who are obviously working on this as a pioneer project. Thank you, Dr. Aldo, who has joined here, Umanath, Lorenzo, who is part of this team, and also all other people who have joined. I really thank them for taking some time out today and hearing me out. Thank you.
great. All right, then. Thank you, everyone. See you at the next meeting. All right. Bye-bye.
Thanks. Bye.
Thank you.
Thank you. Bye.
Thank you.